Hello all, here in this video I'll explain about invertible functions. So the concept of invertible functions came into existence. That is because when you are defining a function, we are taking domain first. We concentrate on the domain and we say that every element of the domain must have some association with the unique element of the codomain. So now the possibility is, can we define a function from codomain to domain? So that idea gives you about invertible functions. So it is like defining a function, having a function from codomain to domain. Is it possible? So let us see the formal definition of an invertible function. A function f from x to y is said to be invertible if we can find there exists another function g from y to x. This codomain to domain. Initially we had a function from domain to codomain such that f composition g, by combining those two functions, will get identity function I with respect to y. G first means y. G first means its domain, and G composite f, which is equal to identity function with its domain, that is x. The function g, this function, if this is possible to have, that means f composite g is equal to g composite f equal to identity function, then that g is called called as inverse of the function f, and it is denoted as f inverse. F inverse is equal to g, we say. So this is what the definition of invertible function means. If we could find a function from b to a such that here we are mapping one element to its image, we have to map image to its pre-image. If that is possible for all elements of the codomain, then we say that that function is invertible, and the reverse function, whatever we define, that becomes inverse of the given function f. Now to define inverse for a given function, that function should be bijective. Bijective means if it should be both 1 1 and onto. If the function is both 1 1 and onto function, only in that case, and onto function, only in that case we can define inverse a function from codomain to domain. Otherwise we can't define inverse of a function. That is because one oneness will help you to have the definition of the function is every element should have a unique image. Every element of the codomain should have a unique image. This uniqueness is obtained because of one oneness, and due to onto-ness, every element will be covered. Okay, so every element concept, this condition will be satisfied due to the onto-ness of that function. Due to the one oneness, the uniqueness will be satisfied. That is what the requirement of a function, to define a function from codomain to domain. Now let us look into this first example. Under this first example, 1 goes to 3, 2 goes to 5, 3 goes to 7, and 4 goes to 5. Okay, so here in this case, if you want to define a function from b to a, I want to define a function from b to a. As per the definition of the function, every element of the codomain now should have unique image in the domain. So now 3 can go to 1 by defining its reverse by defining it in the reverse order. 3 should go to 1, 5 should go to 2, and 5 should go to 4 as per the definition of f. So this violates the rule of uniqueness. 5 at a time can't have two different images because it is not the requirement of a function. Function says that it should go to unique image. That uniqueness can never be established here because this function is not 1 1. Distinct elements are not having the distinct image. So due to which I can't assign 5 to a single element as per the definition of f. So 5 is going to two different elements at a time. Though 7 goes to 3, this is violated for the element 5. Hence I can't define the inverse of this function. The second condition of the function here doesn't satisfy, hence it is not invertible. Or else you can say that it is not 1 1, hence it is not invertible. I hope you understood. One oneness gives you the uniqueness property of the function, and onto-ness gives you the every element property of the function, characteristic of the function definition. Let us take the second example. Under the second example, g is taking 2 to 3, 4 to 1, 6 to 5. Now in this case, if you want to define a function from b to a, so 1 should go to 4, 3 should go to 2, its pre-image, and 5 should go to 6. Both the conditions of a function are satisfied. Every element is having image and every element is having unique image. At a time, no element will have two different images. So I can define a function from B to A, and that function is called as G inverse. Hence, your function G is invertible. If you can't find such function, then we call that G is invertible. So here G is invertible, whereas in the first case the function f was not invertible. Or else you can say here this function G is both 1 1. You can see that it is both 1 1 and onto, hence the function is invertible. So the concept of invertible function is that you should be able to define a function from codomain to domain. If the function is given from domain to codomain, if you are able to find a function from codomain to domain, then that function is invertible. So here G is invertible. G is both 1 1 and onto. G of 2 equal to 1, because 2 is taken to G of 2 equal to 3. 2 goes to 3, G of 4 equal to 1, G of 6 equal to 5. So G inverse of 1 equal to 4, that is how to write it. G inverse of 3 equal to 2, where 3 goes to, G inverse of 5 equal to 6. Let us take a few examples. That is the first one. If f is a function from R to R given by f of x equal to 4x plus 3, show that f is invertible and find f inverse. If you are just asked to show it is invertible, you can go with the other method, like if you show f is 1 1 and f is onto, then you can say that it is bijective, hence it is invertible. They are asking you to find f inverse also. Therefore, the composition of two maps is the better way to show that it is invertible, and also to find the inverse of the function. So, in case if function is given to you, first you have to take that function as a new element y. So, what this function says is f is taking x to 4x plus 3. X is gone to 4x plus 3. That 4x plus 3 I am naming it as y. Now you have to find out where this y is taken. Y is to be taken to x. You have to find out how that x looks. They had given how this y looks. This is your image. Image is in this form. Now you have to find out how the pre-image looks. Pre-image looks like, that is y equal to 4x plus 3. Pre-image is nothing but x. Y is the image. Now x equal to, solve for x. This looks like y minus 3 by 4. This is the pre-image. This clearly belongs to R, because y is an element of real numbers. So clearly y minus 3 by 4, this also belongs to R. So now I have to define a function, because inverse is always like that. X is going to y means y should come to x. That is in the reverse way we are defining a function. So define a function. Now we'll found out how the pre-image looks. So define a function g from R to R given by g of y equal to y minus 3 divided by 4. Okay, this y goes to y minus 3 divided by 4 for all elements y belongs to the codomain. Okay, R. Now you have to find out g composite f of x. You should get it as identity. F composite g of y, you should get it as identity. Okay, identity in the sense, if input identity function means f of x equal to x for all x belongs to the domain. Okay, if the input and output both are equal, both are same, in that case we call that function as identity function. So g composite f of x I have taken, because g of f of x, f input is x, for g input is y. G of f of x is 4x plus 3. Substitute g of y, in the place of y you have 4x plus 3, that substitute here. 4x plus 3 minus 3 divided by 4. 3 minus 3 cancels, 4 cancels, you will get x. Input x, output is also x. Therefore, g composite f is an identity function with the domain of f as R. So I into R, IR. Similarly, you find out f composite g of y. So f composite g of y is nothing but f composite g of x I don't write, because the g is having the input y. F of g of y. G of y is y minus 3 divided by 4. So f of x is given by this. F of x is we have 4x plus 3. f of x is equal to 4x plus 3. So in the place of x you have y minus 3 by 4. In the place of x on the RHS also you substitute that. 4 cancels, minus 3 and plus 3 cancels, you will get y. So input is y, output is also y. So f composite g is also an identity function with the domain of g as r. Therefore, both the conditions are satisfied. G composite f is also identity function. F composite g is also identity function. By combining these two functions in any form, we will get an identity function. Hence, f is invertible, and f inverse of x is equal to g of y. You can either write it as y minus 3 divided by 4, or else you can convert it into x. F inverse of x is equal to x minus 3 by 4. So always you remember the inverse of the given function is always its pre-image. How the pre-image looks like, that you have to find out. That gives you the inverse of the given function. So here we got f inverse of x is equal to x minus 3 divided by 4. And one more property is that if you get f composite f equal to identity, a function's composition with itself is giving you identity, then f inverse is equal to f. Means f is the inverse of itself. I think you can find it in the, like, f of x is equal to identity function x. So f composite f of x is equal to f of x, which is equal to f of x. F of x is nothing but in the x you will get. Input is x, output is also x. So in the case of this identity function, its inverse is itself. F inverse is equal to f. Identity function is nothing but it is a straight line passing through the origin. This is your y equal to x, straight line passing through the origin. So its inverse is the given function itself. So if you get f composite f equal to identity function, then f inverse is equal to f. You can plot the graph of a 4x plus 3, and you can find its inverse using the graphical method also. Then you will get to know what is meant by the inverse of the given function using the graphical method. It is the reflection, it is the mirror image of the given graph or given function with respect to the line y equal to x. So that is what the, with respect to the line y equal to x, that is because we have to get here identity function. So identity function is always given by f of x equal to x or y equal to x. So if you have any graph of any function like this, any graph, you have to consider, suppose if you get any function here below this, it should be the mirror image, then that graph is called its inverse with respect to the line y equal to x. So it should be a mirror image. Graph should be a mirror image of the given function with respect to the line y equal to x. So this is all about invertible functions. The concept of invertible functions exists only when the given function is both 1 1 and onto, or else the given function is a bijection. So in that case only we can define inverse of a function. Thanks for watching.